Today we're going to dive into a question that might have popped into your head while flipping through a high school chemistry book, or just out of nowhere, like a spark. Something on the level of crazy cool. What if, in the history of science, imagine a scientist suddenly had a brilliant, wild idea? What if they threw all 118 known elements of the periodic table, from hydrogen to oganesson, into a giant blender? Yeah, you heard that right. Like they wanted to make a Mendeleev stew. What do you think would come out of it? A magical potion? A tasty atomic soup? Let's take it step by step and lift the veil on this big mystery together and see what this sci-fi-ish experiment really has in store for us. I promise, by the end, your mind will be blown. Okay, before we dive head first into this atomic circus, hold on a second. First of all, we need to clear one thing up. We'd need a container, not just any container. Something that won't melt from heat, won't react with anything, won't pop like a balloon. Something like Tony Stark's armor, but 100 times tougher. Because believe me, friend, without something like that, the game's over before it even starts. Now imagine we have that super container. We start adding the elements. The first thing that's obvious, they're very different faces. Gases like hydrogen, helium, nitrogen, and oxygen, that bully fluorine and menacing chlorine, and the rest of the noble gases, calm and trouble-free, begin to wander around and spread out through the space, mixing with one another. Down below, liquids like silvery mercury and dark reddish bromine gather in a corner. The rest of them, the solids, run the gamut from those soft, highly reactive metals like sodium and potassium, as if just sprung from prison, to heavy, dignified metals like gold, platinum, lead, and of course, Mr. Uranium. Right away, even before you get to the cool chemical reactions and the big fireworks, a bunch of little and not so little things start happening. For example, those naughty alkali metals, sodium and potassium, just need a whiff of moisture, which will certainly be in that mixture unless we're in absolute vacuum, and that's a whole other story. And they spring into action, reacting rapidly and producing hydrogen gas. Now take that innocent hydrogen gas and put it next to oxygen, always ready on the scene, and add a tiny spark. Yes, a little explosion. Right at the start, we'd have a blast that would shake things up. Of course, I call it little when we're only thinking about sodium and potassium. When you're talking about all 118 elements, the situation is very different. Very. Now let's get to the main act, chemical reactions. This is where the real show begins. Some of these elements simply cannot stand each other. Take fluorine, the gangster of the periodic table. It reacts with almost anything you can think of.
And what reactions? Explosions, fires, smoke, and chaos. Now put that angry fluorine next to the alkaline earth metals like calcium and barium, or even other metals. The result is an industrial-scale fireworks display, producing a whole slew of different salts and releasing an amount of energy that could wipe out a small town. It's like throwing a massive rowdy party where everyone starts brawling.
Oxygen is the ultimate accelerator. Many elements, especially metals, are kind of in love with oxygen, and the moment they see it, they rush into oxidation reactions. What does that mean? Burning, rusting, and lots of other exothermic reactions. Now imagine the awful heat that produces. It spreads to the other elements. The temperature of that blasted mixture begins to climb, not by a few degrees. We're talking hundreds, maybe thousands of degrees Celsius. At those temperatures, most solids can't take it, and they melt. Liquids start boiling furiously, and gases, don't get me started, expand wildly and even more violently than before. The pressure on the walls of our magic container shoots through the roof. But did you think the story ends there?
Oh no, my dear. Some of the main players haven't even entered the stage yet. There's a group of elements that have been sitting quiet and calm in a corner. But once they get involved, nothing and no one can stop them.
I'm talking about the radioactive elements, from uranium, thorium, and plutonium to those super heavy, unstable elements like oganesson. They begin to decay on their own and emit alpha and beta particles and gamma radiation. What does that mean? It means our hellish mixture, which was already extremely hot and high pressure, now becomes lethally radioactive. It's like taking a stroll through the heart of a nuclear reactor as it blows up. A full-on hellscape, both burning and radioactive. Those gamma rays are pure concentrated energy themselves, and they can act like scissors, severing chemical bonds between atoms and sparking new, unpredictable reactions.
Alpha and beta particles start shooting out like invisible bullets, slamming into the nuclei of other atoms and transforming them into different elements.
What does that mean? It means our beautiful, neat periodic table is no longer that tidy, organized chart we know. It's turning into something like cosmic Play-Doh, constantly changing shape. One element becomes another, and this insane cycle keeps repeating. This is what you'd call nuclear alchemy in action, but not the kind that tries to turn copper into gold. This version is far more violent, ruthless, and utterly uncontrollable. It's as if nature itself has gone mad. Now let's take a deeper look at this catastrophe. All that energy released from non-stop chemical explosions and nuclear decays, where does it go? Obviously, it's all converted into heat, light, and radiation. The temperature of our bizarre mixture skyrockets so high that we're no longer talking about ordinary liquids and gases. Most likely, the atoms can't even hold on to their electrons anymore. Those electrons break free and turn into ions, which means we now have plasma, the fourth state of matter, the same stuff stars are made of, an ultra-hot, ionized soup of free atomic nuclei and wandering electrons, spewing out powerful electromagnetic waves and deadly radioactive radiation at the same time. Basically, we've created a miniature version of the chaos that happens inside a star's nuclear furnace, except here, it's far messier, more chaotic, and a whole lot more dangerous. And our so-called magic container? No matter if it's made of vibranium or any other fantasy metal, it will eventually give in under such insane pressure and heat. If that demonic mixture somehow leaks out, which, given that much energy, it almost certainly will, since no material in existence could withstand it, the environmental disaster that follows would put even the wildest sci-fi apocalypse to shame. The entire surrounding area would become drenched in radioactive and toxic materials, remaining uninhabitable for thousands of years. It would be as if we dropped a piece of hell itself onto Earth. Now, here's the big question. Would we actually end up with a mixture? Or would it be more like a full-scale battlefield where elements tear each other apart, transforming into new ones and creating total chaos? Honestly, the second scenario is much closer to reality.
After all the rapid explosive reactions die down, and after the temperature finally cools off, which, mind you, might take thousands of years, what would remain is probably a blend of the most stable isotopes of various elements, trapped in a kind of glassy or ceramic matrix made of oxides, silicates, and other ultra-stable compounds.
Meanwhile, most of the heavier elements would have decayed into lighter, more stable ones. The result would be something resembling the strange matter ejected into space after a supernova explosion, but on a much smaller, denser, and more chaotic scale.
Interestingly, something similar, though on a far gentler level, has actually happened in nature. About 2 billion years ago, in a uranium deposit at a place called Oklo in Gabon, Africa, a natural nuclear reactor started running on its own because of high uranium concentration and groundwater presence. It stayed active for hundreds of thousands of years.
So, mixing all the elements of Mendeleev's periodic table is basically like opening Pandora's box on a cosmic scale, unleashing unbelievable chaos, from the first chemical explosions and hellish heat to relentless nuclear decay, plasma formation, and elements constantly transforming into each other. A deafening symphony of destruction and disorder.
And the final result? A mass of super radioactive, blistering hot, unpredictable, and probably very stinky material, made of countless compounds and brand new elements that look nothing like the ones we started with.
If you enjoyed the video, please give it a like and subscribe to support the channel. Thanks for watching and for your support.